guys, welcome back to Untitled Lectures, and today I want to focus on looking at example 5, which is one of my examples for Young's modulus questions. So these questions are tending on the more difficult sides because if you have gone through most of the K-Pass papers, you'd have noticed that you were typically asked to state definitions of things like tensile stress, tensile strain, Young's modulus, right? So tensile stress, just to recall, is a force acting per unit area, and the unit would be Newton per meter squared or pascals, and is given by sigma, which is F over A. Strain is a ratio of the extension to the original length. And Young's modulus, of course, is a ratio of stress to strain. One of the things that they like to bring a lot is if they give you a stress-strain graph and they ask you to get the gradient. And the gradient would, of course, be Young's modulus. And because the stress is given by sigma, which is F over A, and the strain is epsilon, which is the extension over the length, then we can combine that to get a simpler formula for Young's modulus, which will be the force by the length over the area, cross-sectional area multiplied by the extension. Now, cross-sectional area typically for a wire is given by pi by the diameter squared over 4. So they can ask you to manipulate the equation a little bit, and it's more or less straightforward. They tie the topic in with Hooke's law, and if the graph is linear, then it obeys Hooke's law. It undergoes an elastic deformation where the molecules tend to, on experiencing that deforming force, tend to deviate from the equilibrium position. And of course, if it's applicable to, let's say, a wire, those are categorized as crystalline materials, and they tend to have molecules arranged in a lattice. So when the deforming force is applied, it causes the planes of molecules to slide against each other. And of course, you may be given a graph and it may be asked to state if it's ductile, polymeric, or amorphous, right? And those things you could look at in my previous video. So to the matter at hand of one of the examples, it's a little bit challenging because it's a little bit unusual. So I thought to highlight it. A steel wire of length 1 meter is fixed horizontally between two supports 1 meter apart. So that makes sense, right? And when a mass of 8 kilograms is hung from the midpoint of the wire, the middle of the wire sags at a distance of 2 centimeters, right? If the diameter of the wire is 2.8 millimeters, determine the Young modulus. So once we talk about Young's modulus, the first thing that should be coming to your head is the formula, right? So I've always taught my students, it does not matter how eccentric or challenging the question may present itself, then you have to break it down and bridge the gap from what you know. So the first thing I would think about is what is the formula for Young's modulus? And that would be E is stress over strain, FL over AE. Then I will go to the information. And this is where the concept of apple picking comes in, where I'm going to pull out the pieces of information from the question and try to see if I can fill it in the formula, right? And this is before I have even looked at the diagram, okay? So I have diameter, okay, good, so I can get area. I'm told that it sags 2 cm, okay, so I look at my diagram and see how that fits in. And I have force, so the mass could give me weight, which should give me force. So far looking like I maybe have F and I have A. All right, so let's look at the diagram now. So you have this wire, and the midpoint of it, when you place the weight, it causes it to sag. So now you have tensional forces acting, right? So what I did, and then you have a weight attached. So my first concept was get the formula for Young's modulus. Now I look at the question, what is given? Oh, and I was told the length of it was 1 meter, right? So then I don't have E and I don't have F, right? But I have to find it. So I could use Pythagoras Theorem because I know that the wire sagged 2 cm from its initial position when the weight was brought to it. So I realized it was a right angle triangle. So based on that, I could get the hypotenuse, which was BC, and then I'm going to get the extension from that. So the length, right, I could say that this extension is BC minus, 50 cm. Right? So when I worked it out, I got by Pythagoras Theorem, right, 50.04. So the extension E, right, upon the weight being loaded to the wire was 0.04 centimeters. Now, because I'm considering both sides of the wire, I have to double that. So then my extension became 0.08 centimeters. So I want to determine the tensional force, right? So I have the weight, which is mg, all right, and so before, remember, I told you that was a force, right? But I have to remember when I looked at my diagram that I have to identify now the tension. Now, because the wires were clearly at an angle, I have to resolve the tension. So now I am looking at the component of the tensional force that balances the weight, which will be 2t cos of theta, right? Because remember, it's two sides of the wire, which is equal to the weight. I, of course, had the angle now. I found it by 2 over, right, BC, because remember the height of the triangle here was 2 centimeters, and then the hypotenuse here was 50.04. So I could have found cos of my angle. So W is mg over 2 cos theta, and you work it out. And then, of course, E is FL over EA. So what we did was we let the tension be equal to the force, right? So when I worked out what the tension was, I divided it by, I found the extension, and then I solved for E. So I'm just going to leave it here for a few minutes. So let's kind of recap what we looked at. So we got a question where a wire was loaded, and there was a sagging at the midpoint where the load was attached, and it formed a triangle. So we have the height of the triangle and we have the length of the base, and based on that we used it to get the extension of the wire. Using Pythagoras Theorem, the extension of the wire had worked out to be close to 50.04. So then the extension would be 0.04. And for both ends of the wire, due to the load being attached, it totally stretched 0.08 centimeters. So for Young's modulus, now I have the extension. The length of the wire was originally given as 1 meter. Because I had the diameter of 2.8 millimeters, I could have worked out the area, pi d squared on 4, and I convert d to meters. So I'm working in SI units. And the challenge now is to get the force. So let's go back up to the diagram. So here, when I talk about my force, I realize that there is a tensional force. And I balance, because remember, I'm saying that it's not moving, right? Where you can have the tensional forces can be resolved. So 2t cos of theta is equal to the weight. And I could solve for t, because t would have been my force. Okay? So you could solve for t, right? That's the tensional force in the wires. And then T would be F, and then you work it down. And the Young's modulus of the material worked out to be 1.993 by 10 to the 11.